Hi everyone, I'm Jyotismita Adhikary. I'm a final year PhD student at National Center for Nuclear Research at Warsaw, Poland. My supervisor is Sebastian Trojanowski, and I am currently working on looking for sub-GeV WIMP-like dark matter in relativistic regimes, which includes colliders as well as astrophysical objects, and I'm also interested in complementary signatures in cosmology. So, coming to the talk, my talk is probing of neutrinophilic scalars in the era of high energy muon beams, and it is based on the paper that's already published here. The link is here, and it's with Kevin Kelly, Felix Ling, and Sebastian Trojanowski. So let me go to the outline of the talk. So first, I'll introduce what neutrinophilic scalars are, and I will next talk about what dark matter models these neutrinophilic scalars can couple to and hence can be probed via them. And then I'll discuss the signature itself that can be probed in the muon collider. And last but not the least, I'll discuss about possible backgrounds and its mitigation. So let's go to the model first. So what is the model? So we introduce a scalar phi that carries a lepton number of -2, and it couples to the standard model that involves a dimension 6 operator, as you can see here in the Lagrangian, where L alpha, L beta are lepton doublets, H is the Higgs doublet, and these alpha and beta for our case, it's equal to mu. And after electroweak symmetry breaking, we get coupling of phi to neutrinos with the coupling constant lambda. And here again, it will be lambda mu mu for our case. Okay, moving on, let's talk about the dark matter candidate itself. So this phi can have different kind of dark matter candidates that it can couple to, such as Dirac fermion dark matter with lepton number +1, which undergoes freeze out. We can also have complex scalar with lepton number +2/3, which also undergoes freeze out, and these two models have been introduced in this paper, which I link here. And we have the sterile neutrino dark matter, which was first introduced in the 1980s. So the idea is that active neutrinos have mixing with sterile neutrinos, and hence effectively it can oscillate to sterile neutrinos up to the point of neutrino decoupling. But this mechanism at the very basic case where there is only a mixing between nu A and nu S has already been excluded by X-ray experiments. Why X-ray experiments? Because this sterile neutrino can later decay to active neutrino and gamma, and this gamma falls in the range of X-rays, which has already been excluded. And the mixing parameter theta it can only be lower for it to be not excluded by X-ray experiments. And for that, if we have extra interactions between standard model neutrinos, then we might evade this X-ray constraint. So this is where phi comes in with extra interactions, so we can have lower coupling, which will produce the same amount of dark matter as Doddelson withdrawal mechanism. So here is the third candidate. Moving on, we go to what we are looking for at the muon collider. So let's look at the diagram here. Let me take a moment to explain everything. So what we have in the muon collider is a collision of mu minus and mu plus at the interaction point, and these mu plus and mu minus are highly accelerated. But one thing also to note is that these muons, we know they decay, right? So we look specifically for this kind of signature. Now note that this is not only limited to mu minus. We can also look for mu plus decaying to exactly the opposite particles here. That doesn't change anything. But let's just say we probe this direction first, or only this direction. It's not dependent on the direction, our theory, right? So we have mu minus decaying to nu mu e minus nu e bar, right? And this is in the, not exactly at the interaction point, but at the straight section before, around the interaction point. This is where the amount of decay is maximum. And so we focus specifically on these new mu's. So these are muon neutrinos, and since they are neutral, they are not gonna be bent by the magnets that will be placed here in this region, as you can see from my cursor. But they will travel in the forward direction, where we propose to put a detector around 100 meters from the interaction point, but this can change, of course. Okay, let's just say it's 100 meters from the interaction point, and we study what happens when these new mu interacts with the target material, with the detector material. So because of the extra coupling with phi, we can have a positive wrong sign muon signature, because generally, if you note in the standard model, we have nu mu, w, x, and this goes to mu minus and x prime, right? But because of this introduction of nu phi, we can have this extra phi going out, right? So this is our signature. So let me just talk about muon collider, why it's important. I already discussed about this, but to know about the sheer number of neutrinos, we should look into it. So what is the muon collider? We envision a 4.5 kilometer storage ring into which about 10 power 13 muons will be injected each second. And again, as I said, the largest flux of neutrinos will be near the straight section around the interaction point. I know it looks like there is no straight section, but the diagram is not up to scale. And then we assume that the straight section has a length of about 10 meter, and that results in 10 power 10 neutrinos per second, which is a huge number. Okay, now coming back to standard model, we know we have this extra phi going out, and we have this wrong sign muon signature, but at the same time, we definitely will have standard model background from nu mu and nu e bar, as well as pions that are produced from hadronization, right? So we have different backgrounds, neutral and charged current nu mu events, which is via W and Z, which produces mu minus instead of mu plus. And then again, neutral and charged current nu e bar events. I missed a bar here. Anyway, and then in all these signatures, the mu plus can only come from this hadronization part, right? So one thing to note is that this mu plus will have lower energies as compared to the mu plus produced there. So we take into account different variables to constrain the background. For that, we select several variables like energy of mu plus, E visible, then transverse momentum of mu plus, and then the missing momentum, and then the angle between transverse momentum of mu plus versus the transverse momentum of missing components, which include neutrinos and phi. So here are the 4 different plots where we show the 1D observables. Looking at the plot, in the y-axis, there is a number of events predicted per year. Here are the variables. We have E mu plus by E visible, PT mu plus, PT missing, and then the angle between PT mu plus and PT missing, which is delta phi. And all these plots have 4 different colors which correspond to charge current prompt decays, charge current displaced decays from pions or nkaons here, the neutral current prompt and neutral current displaced decays for a specific mass of 1 GeV and coupling of 0.3, and for different cases different coupling, just to show it on the plot how different observables behave. Okay, so proceeding to the 2D observables, here also we consider PT mu, relation between PT mu plus and del phi. We plot both background signal and the ratio, and we put a cut here, as you can see, to get rid of the background. Moving on, we have the background mitigation, the table, cut flow table. So first of all, as I mentioned, that the energy of mu plus produced from these kind of interactions would be way higher than the normal standard model background. So we put a cut of 100 GeV on the mu plus energies, and then we also have energy of mu minus. So energy of mu minus, why do we put a cut? Because if we look at the signal, background, then we have this specific process where we get mu minus, and this mu minus will have a high energy. So to get rid of the charge current nu mu background, we can put a cut on the energy of accompanying mu minus, right? So we'll reduce some events, and accordingly we also use some ratio of E mu plus and E visible, because it turns out that if we consider the ratio, as we go to higher masses, the contribution of mass in terms of background, it cancels out. So it's better to use E mu plus by E visible rather than one or the other. Then we also have charm veto, or about 80%. And then we have 2D cuts, PT mu plus versus delta phi. And yeah, here are the numbers. And lastly, we put a BDT cut to finalize the numbers. And with this, we have this plot, which is the sensitivity reach of muon collider towards this neutrinophilic scalar after each cut. So here, if you look at the dark dotted line, and this is with no background, then we move further higher up as we put the different cuts. And so this is our result. This is for 10 kg detector. So our final sensitivity reach is here, where we have 2 lines specifically, if you note, is for 10 kg per year and 10 ton, so this is a bigger detector, per year at 3 TeV center of mass energies of the muon collider. Right, and you'll note this muon collider age to invisible line also, which I'll talk about next. But first, let's focus on the different dark matter candidates. So complex scalar, Dirac fermion, and steraneutrino, and all of these falls within the reach of the muon collider. Right, so we can technically indirectly probe these dark matter candidates via phi. So moving on to the orange line. So what is that? So if we move back to the Lagrangian, then after electroweak symmetry breaking, we can also have term like this, where there is a coupling of phi to the Higgs, right? So we can have Higgs decays to nu phi. So this is Higgs to invisible decay, and for the muon collider, our sensitivity reach lies here. So this is my result, or our result, and I will move to the conclusions now. So with this work, we have tried to probe neutrinophilic mediator with high energy muon beams, and the muon collider mu detector would be specifically capable of searching for a neutrinophilic mediator phi through mono neutrino scattering process. As I discussed earlier, we'll have a positive signed muon, and it exceeds the searches from other terrestrial approaches for M phi in the range of few MeV to tens of GeV range, as you saw here. And then the search of this mediator will also open windows to probe dark matter models that couple via mediator to the standard model of particles, which I discussed about already in terms of Dirac fermion and complex scalar, as well as steraneutrino dark matter. And lastly, neutrinos have always been a loose string in the standard model, and there are plans to study neutrino physics in the muon collider along with PSM physics. And this brings me to conclude my talk. Thank you so much everyone for listening. And at last, my parting words are that I'm finishing my PhD next year, and I'm actively looking for postdocs. So if anyone shares similar ideas or have similar interests, I am really open to network and collaborate in the future. Thank you so much. Bye.